So today I'm going to be talking about okay, intelligence efficiency, right? Um, and how we can maximize it. I'm going to start off with three graphs, and I want to talk about where we are today as an industry and where I think we should go. Um, so where are we today, right? ChatGPT came out, LLM boom occurred, intelligence skyrockets over time. We've seen this, right? We've all seen the benchmarks. Intelligence is only increasing, it's increasing at an exponential rate, right? Additionally, with that, we've seen tokens skyrocket over time. We've seen token maxing occur in the industry, and we've seen industry as a whole really adopt LLMs into their production processes, causing this to occur, right? But additionally, what I think we've seen is that these models are getting smarter, but they're not getting more efficiently smart, right? The more money you're paying, we see like the state of the art over here, right? This is the Fable. This is like maybe last year's models. The more money you're paying for intelligence is actually having diminishing returns, right? And this is not necessarily what the world was sold, right? We were sold with LLMs that you could buy intelligence at a unit economic price, but what we're actually paying for is tokens, right? And this is not true, right? We all know this as technical folk. We know that intelligence does not equal tokens. Yet people are trying to buy this, but are actually purchasing this, right? And there's a fundamental difference there that exists, and I think will actually come to bite the model providers in the ass a little bit, right? We see this logarithmic curve to some extent, while folks want a more linear curve, right? Some data to back that up. I work at Ramp, like Dorkesh said. So we see a lot of this in the data as well. Just some stats is that we've seen a 13x monthly token spend since January 2025. And we've also seen some political things happen in the technological space, right? We've seen Uber, we've seen Meta clamping down on this token masking and really making sure that this exponential doesn't necessarily continue as it affects the bottom line. We also recently did a a version of Sweetbench of Ramp, and we saw this like more logarithmic curve where intelligence is actually getting less efficient over time, not more efficient. And some of the research I've been doing personally is how can we make sure that this graph is more linear rather than more logarithmic, right? And what I found is that context seems to really be the key in order to provide for the models, we provide more context, they tend to become more efficient and need less work to complete the same processes. I want to give some mathematical foundations of this. So the way I think about LLMs, and AI as a whole, and agentic processes, is that they are really entropy reduction machines, right? So entropy is a measure of chaos in a state. And if you think about LLMs, what they do is they take very high entropy states. They take PDFs, they take information from the web, they take information from very scattered fields and a prompt, and they organize it into what the user is asking for, right? They fundamentally reduce the entropy of state. I think out of this field of thought, we can actually derive equations that show how introducing context into the field makes LLMs and AI as a whole very more efficient. So there's two fundamental views of entropy. There's an information theoretic view of entropy, which is a Shannon entropy definition, which says that the entropy of a state after an observation is fundamentally reduced. I think this is pretty obvious, right? You have some chaotic system, you measure it, you understand a little bit more, and so the chaos of the system, at least our local representation, is reduced, right? Additionally, the thermodynamic view of entropy says that the amount you can reduce entropy in a system is upper bounded by the amount of work you put in. And combining these two equations, we can see that there's an upper bound on the change of entropy in a system, both from the work you put in and from the information we already have about the system. The way I explain this to people is like, let's say you're cleaning your room, right? You have to know where the dirty clothes are to put in the work and put them in the right place, right? So to reduce a chaotic system to a less chaotic system, you have to have both. And I think modern LLMs really focus on how much work we can put in, right? Chain of thought, reasoning. We see that the more work you put in, you can reduce the entropy system. We've seen it. We know it's not linear, but it's true. But they're not necessarily focusing on the information piece of it all, right? And I'm gonna give 3 examples to try to illustrate how providing context, memory, information, whatever you want to call it, into the system, particularly in the latent space, can make LLMs more energy or more intelligent, efficient. Okay, and to give some context, the current methods in the field to provide context are like RAG or memory. But we all know that these have problems, right? They don't scale that well. They're typically used for needle and haystack tests or semantic search tests, and really struggle with multi-hop reasoning queries, right? Where multi-hop reasoning, if you don't know, is taking a bunch of facts, putting them together, and constructing a logical answer from that. They also both happen in token space, which is fundamentally constrained for the models, rather than a latent space, right? And I'm going to talk about 3 examples in the latent space that I believe are efficient ways to convey context to the underlying models and increase the intelligence efficiency. So this is going to be in multi-agent systems. The chalk is getting small. Okay. In the context window, and as inputs, right? So these are like the 3 fields of research I've been looking at over the last few months, and I want to explain them. So let's start with multi-agent systems. So I'm going to give a model of multi-agent systems and then explain how it can be improved and the results we've seen from that improvement. So multi-agent systems, we can say, pretty abstractly, there's like a supervisor agent, right? And then can spawn worker agents, right? I'm pretty sure uh, everyone knows about this kind of stuff, right? And they all complete a task, but let's say this is time down here. Um, the problem with this, right, is it's extremely inefficient. The amount of tokens that this uses is really astronomical. And in the current economic state where token maxing is largely unsustainable, we need to fix this somehow, right? Additionally, the supervisor agent, as it's doing work, is generating context. It's exploring the system. We also see that the worker agents are all generating their own context itself. And this is not shared in the global state, right? A context a worker discovers here might have been discovered here, and now we're putting in extra work and becoming very inefficient, right? So part of the research I did is, let's say we share context. We maintain a global state of context, which I did as a global KB cache that was shared among the agents. And we can, when we spawn a new agent, take the task that it's spawned with, filter out the information we need from the KB cache. We did this with a compression algorithm, essentially. And then spawn the worker with this initialized KV cache that essentially contains the context of the system that's important to the worker, right? When we judge this system versus the system without context sharing on a multitude of tasks, we saw in total there was a 42 to 57% reduction in worker agent tokens and a total reduction of 21 to 31% total tokens with the same accuracy, right? So they become highly more efficient just by producing shared context, introducing information into the global system, right? Additionally, some work I also did is about like in context learning, right? We've all seen like DeepSeek's released the sparse attention model, right? Or hopefully we've all seen that. And we've seen that sparse attention is really taking industry by storm. It makes sense, right? We need a more efficient way than dense attention. But the way I want to investigate sparse attention is modeling it as a re-ranker model, right? Fundamentally, if you think of sparse attention, it's looking at one token saying, what information of the past tokens are necessary in order for me to generate the next token, right? And this is very similar to how re-ranker models work in RAG. And so I wanted to say, okay, if this could model a re-ranker system, it would be evidence that more efficient model was partly at least because of accurate context retrieval over its own token space or latent space, I guess. And so what we did is we took the queries and the keys generated by the Lightning indexer from the DeepSeek model, and we computed document scores over a question answer data set that was like multi-hop to try to see if it would accurately get the right documents for a question. I'm just going to write the equations of how we did that. Um, feel free to like come up to me after and like ask about any of these because I'm going pretty quick. But essentially we took the ReLU of the cost of the normed query over the queries. Like basically we have like a data set with a bunch of documents and multiple choice questions over those documents. The queries are from the questions in the multiple choice data set. And we did this with the keys from the normed keys from the docs itself. And then we could compute a score from the like for each doc that was just a sum of these cost scores times each head, and then we just took the mean over all tokens in the doc, right? And what we found is that using this like pretty simple scoring method from the sparse attention mechanism, we actually match or beat state of the art current re-ranker models, showing how this essentially mirrors a re-ranker and is essentially just context retrieval over the context window. So here I just want to reiterate, 2 minutes left, but I just want to reiterate that these are both examples of fundamental information introductions to the system, context retrieval, that make the full system much more efficient, right? Sparse attention is way more efficient than dense attention. Multi-agent systems, we showed that there was a huge reduction in average token choose in order to get the same result. And the last thing I'm going to talk about is some work I've done doing with the Snap Lab at Stanford to reduce the number of tokens we actually need in the input rather than the output, while maintaining state-of-the-art results. So we have this idea of when doing LLM systems, why do we have to put the entire doc in the context window when doing like RAG? Instead, what if we just treated memory or context injection as a modality as we do text, as we do image, as we do video, where it's a full modality onto itself? And how would that work, right? So what we did is we built a memory module, is what we called it, where we took docs in as well as a query. This is over like a multi hop reasoning data set, right? Um, we built an architecture that took these in, produced 16 latent representations, right? And then injected them directly into the frozen LLM. Here we use Quen 8B. Um, and our theory was, okay, if we can inject 16 latent state representations that tend to take the information in the docs from the query that is necessary, like how will it perform, right? Directly into the frozen LLM. What we found is using the Trivia QA dataset, we actually beat RAD 50, where we took the 50 most relevant docs to the query and injected them directly in the context window in the token space by a fair margin. So using this approach, we could inject the 16 latent space representations and get a 63% exact match over the, like I said, the Trivia QA dataset, while RAG 50 got a 55% exact match. And fundamentally, this actually used 372 times less tokens representations in the input. So it's doing better, right? It's more intelligent, efficient, while using 372 less tokens. So it's incredibly more efficient just by introducing the correct context through this method in the latent space. Okay, so I hope that I've convinced you all that latent space representations of context and context retrieval is incredibly important in the LLM sense. I want to leave you with like what I think would be the holy grail of a model that could introduce context accurately. I think it should be low latency so it can be used at inference time. I think it should scale over large corpuses. And I think that there should be essentially zero switching costs to the base LLM so that when the next model came out, you could introduce the most state-of-the-art reasoning model while still maintaining this context introduction into the global system. These are like research topics that I'm exploring so that we can introduce them in the large AI tooling systems that we're using at RAMP, such as Inspect, where we're actually only generating more context than we ever have before. Thank you.